Time? We feel it flowing. Seconds tick by, days pass, years vanish. But what if everything we believe about time is an illusion? What if the past, present, and future all exist at once? This may sound like science fiction, but in physics, time isn't what it seems. Einstein's theory of relativity shattered the idea of a universal now. In his view, time is woven together with space to form a four-dimensional fabric called space-time. Depending on how fast you move, or how close you are to massive objects, time stretches or compresses. This means your now might not be someone else's. To a person moving at near light speed, events you call the future may already be in their present. In other words, simultaneity is relative, but it gets deeper. Many physicists support the block universe model, where time doesn't flow at all. Instead, all moments, past, present, and future, exist simultaneously, like pages in a book. We only experience time as flowing because our consciousness moves through it, moment by moment. It's like a film reel. Every frame already exists. We just perceive it in sequence. If this is true, then the future already exists, waiting for us to experience it. Destiny, perhaps, isn't written in ink, but in geometry. And yet, we feel the arrow of time. Why? This is where entropy comes in, the measure of disorder in a system. The second law of thermodynamics tells us entropy always increases. Eggs don't uncrack. Smoke doesn't return to a matchstick. This gives time its direction, from order to chaos. But here's the twist. The laws of physics work just as well backward as they do forward. So why does time only move one way? Some theories propose that entropy's increase is a result of the low entropy state of the Big Bang. Time's arrow may simply be a feature of our corner of the universe, not a universal truth. Other models suggest that in regions far beyond ours, time could flow in reverse, or in loops, or not at all. At infinity beyond, we challenge the illusion of time because it shapes every part of human experience: memory, choice, fear, hope. If time is not what it seems, then neither are we. Are you a traveler through time? Or a fixed point in a cosmic structure? Does the future already exist? Or do we shape it moment by moment? In the end, the more we understand time, the more mysterious it becomes. And perhaps that's exactly what makes it beautiful. We often think we understand gravity. After all, it keeps our feet on the ground. It makes the planets orbit the sun, and it shapes the large-scale structure of the universe. But what if gravity isn't exactly what we think it is? What if our current understanding only scratches the surface? The strange motions we observe in galaxies, stars moving too fast, gas clouds drifting in unexpected ways, all point to a disturbing possibility. Either there is a massive amount of invisible matter, or gravity behaves differently on galactic scales. This has led scientists to question whether our fundamental theories, Newton's laws, even Einstein's general relativity, hold up when applied to the cosmos at large. Maybe the force we call gravity isn't a force at all, but an emergent effect of something deeper, something woven into the very geometry of space-time. Some researchers suggest modifications to gravity, like MUND, modified Newtonian dynamics. According to this theory, gravity doesn't weaken as quickly as we expect when we move to interstellar distances. If true, we might not need dark matter to explain galactic rotation curves at all. But even MOND has limitations. It works well in galaxies, but struggles with galaxy clusters and cosmological observations. And so, the mystery deepens. There are other radical ideas, too. Some physicists propose gravity is a result of thermodynamic processes, like heat and entropy, rather than a fundamental interaction. Others suggest it's a side effect of information theory, the universe computing its own shape, and gravity being the result. And then there's the boldest question of all. What if we're living in a simulation? In that case, gravity might simply be the algorithmic rule set of a vast cosmic program. But let's come back to what we can observe. Using instruments like the Hubble Space Telescope, the Gaia mission, and ground-based observatories, astronomers are mapping star positions and motions with breathtaking precision. These observations continue to challenge our assumptions. Why do galaxies on the edge of the universe look so mature, so fast? Why is the cosmic web so intricately connected, like neurons in a brain or pathways in a city? These structures seem to follow patterns we don't yet fully understand. At Infinity Beyond, we ask the questions that push the boundaries of human knowledge. If gravity doesn't behave the way we expect, maybe it's trying to teach us something new, something profound. The universe doesn't owe us answers, but it leaves clues in the form of spinning galaxies, bending light, and ancient starlight from billions of years ago. Are we brave enough to follow those clues into the unknown? In a universe with trillions of galaxies, each containing billions of stars, it seems almost certain that life must exist somewhere else. And yet, silence. No signals, no spacecraft, no undeniable evidence. This is the heart of one of the greatest mysteries in science, the Fermi paradox. First posed by physicist Enrico Fermi in the 1950s, the paradox is simple. If alien civilizations are common, why haven't we seen any signs? There are dozens of possible answers, some hopeful, others unsettling. Let's explore a few of the most compelling. We are early. Maybe intelligent life is incredibly rare, and we're among the first to arise. In this view, the universe is still waking up, and life, especially technological life, takes longer to emerge than we think. They're too far away. Space is vast. Even if alien civilizations exist, they may be thousands or millions of light years away. Our signals may simply not have reached each other yet. They're listening, not talking. Perhaps everyone is listening, waiting for someone else to speak, a cosmic stalemate of silence. Or perhaps they use communication methods we don't understand, like neutrinos or quantum entanglement. The Great Filter. One of the darkest theories suggests that there's a dangerous bottleneck in the path from basic life to intelligent civilization. This great filter could lie in our past or in our future. Maybe most civilizations destroy themselves with war, climate collapse, or AI before reaching interstellar maturity. Their hiding advanced civilizations might follow the zoo hypothesis, observing us from afar, but choosing not to interfere. Others may cloak themselves from detection entirely, out of caution or ethics. We're not ready to perceive them. What if alien life is so advanced, so different, that we simply can't recognize it? It may not be biological. It may exist in dimensions or forms we're incapable of detecting. Perhaps the universe is teeming with life, and we are the blind ones. At Infinity Beyond, we believe the silence of the stars is not discouraging. It's motivating. It reminds us that we must be the signal. Until proven otherwise, we are the voice of intelligent life in the galaxy. And with that comes responsibility to explore, to learn, to survive. Because maybe, just maybe, the reason we haven't heard from them is that we're meant to go first. What if the stars you see were only a small fraction of the true structure of the universe? Imagine that everything, galaxies, clusters, superclusters, is suspended on an invisible framework. This is not science fiction. This is dark matter, a mysterious, invisible substance that outweighs everything we can see. Dark matter does not emit light. It doesn't absorb it, reflect it, or interact with it in any measurable way. And yet, it reveals itself through gravity, through the ways galaxies spin, the ways stars move, and the way light bends through space. Without dark matter, our galaxies would fly apart. Their spin would be too fast for the visible mass to hold them together. But because galaxies remain intact, something unseen must be anchoring them. One of the clearest pieces of evidence for dark matter comes from gravitational lensing, where massive objects bend light from more distant galaxies. Sometimes the light curves in ways that don't match the visible mass. The only explanation? Invisible mass, dark matter, is lurking nearby. Another mystery is how galaxies form in the first place. The early universe was hot, dense, and chaotic, yet somehow matter clumped together. Without dark matter providing the gravitational scaffolding, this clumping wouldn't have occurred fast enough for galaxies to form in time. But what is dark matter made of? Is it a type of particle? A new kind of field? Could it be related to the birth of the universe itself? Or perhaps the leftover debris from dimensions we don't yet understand? Physicists have proposed candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos. Each has its allure, and each remains elusive. We've built enormous underground detectors in abandoned mines, and yet we've never caught dark matter in the act. And then there's the possibility that we're wrong altogether, that gravity itself needs a rewrite on galactic scales. Some scientists suggest alternative theories like MOND, modified Newtonian dynamics, questioning if we really understand the fabric of space the way we think we do. But no matter the theory, the evidence keeps piling up. The way galaxies cluster, the way the cosmic microwave background behaves, the sheer structure of the universe, all scream for an unseen force, a hidden skeleton of the cosmos. Here, at Infinity Beyond, we ask, could the key to understanding the universe be hiding in plain sight, tugging gently at everything, yet remaining forever invisible? As we gaze into the night sky, it's humbling to know that 85% of the universe's mass remains hidden, and yet it shapes everything. That's the paradox of dark matter, unseen but undeniable. Thumbnail prompt, English: a mysterious cosmic web of glowing filaments on a dark background, connecting clusters of stars and galaxies. At the center, a shadowy figure or silhouette representing dark matter, holding it all together. Overlay text: what holds the universe together? What if the Milky Way, vast and luminous as it is just the tip of the iceberg? What if the true mass of our galaxy is hidden beneath a dark, invisible shell? Welcome to the mysterious world of galactic halos, massive, unseen structures that surround galaxies and hold the cosmos together. The visible part of the Milky Way, all its stars, planets, and nebulae, accounts for only a fraction of its total mass. Surrounding it is a vast halo of dark matter, extending far beyond the edge of the spiral arms. We can't see this halo directly, but its gravitational pull is undeniable. It's this invisible cloak that holds the galaxy together. Without it, the stars on the outer rim would spin off into space. It acts as the glue, silent and omnipresent, maintaining the Milky Way's majestic shape. But how do we know it's there? The answer lies in orbital speeds. As astronomers measured how fast stars rotate around the galaxy, they noticed something strange. Unlike the solar system, where planets move slower the farther they are from the sun, stars in the Milky Way maintain a nearly constant speed, even at vast distances. This flat rotation curve suggests that something massive, but unseen, is adding gravitational pull. That something is the dark matter halo. And the Milky Way isn't alone. Nearly every galaxy we've studied seems to be wrapped in one. These halos don't emit light, but they can bend it, distort it, and guide the motions of billions of stars. Some scientists think these halos could be filled with exotic particles, like WIMPs, weakly interacting massive particles, or perhaps made of undiscovered physics entirely. Others theorize that the halos are more than spherical shells. They might be clumpy, asymmetric, or shaped by cosmic collisions. One fascinating possibility is that our own galaxy's halo may be interacting with those of neighboring galaxies, like Andromeda. This could create gravitational bridges or streams of dark matter flowing between them, shaping the future of both galaxies long before their predicted merger. At Infinity Beyond, we're driven by these invisible questions. How large is our halo? What's inside it? Could it hide rogue black holes, ancient relics, or something beyond our current physics? What's certain is this: the night sky is only a sliver of the truth. The real structure of our galaxy lies in what we can't see, a hidden skeleton of dark matter, shaping the stars in silence. Among the most mysterious features in the observable universe is something so subtle and yet so strange that it defies explanation. It's not a black hole or a distant galaxy. It's a cold patch in the sky, a place where the universe is just a little too quiet. This is the CMB cold spot, a region in the cosmic microwave background, CMB, that is significantly colder than the surrounding space. The CMB is the leftover radiation from the Big Bang, a snapshot of the infant universe, glowing faintly in microwave light. And in that otherwise uniform glow, this cold spot stands out like a scar. So, what causes it? One theory suggests it's the result of a supervoid, an enormous region of space with fewer galaxies and less matter. As photons from the CMB pass through this underdense area, they lose a tiny bit of energy due to the integrated Sachs-Wolf effect, arriving at Earth slightly cooler than expected. But here's the problem. The cold spot is too cold. Even accounting for a supervoid, the temperature drop is more extreme than our models predict. This has led some to wonder, are we seeing evidence of something bigger? Some have proposed that the cold spot could be the scar of a cosmic collision, where our universe once bumped into another during the inflationary phase of the Big Bang. If the multiverse is real and other universes exist beyond our own, such a collision could have left an imprint on our sky. Others suggest it may be a topological defect, a leftover wrinkle from the universe's birth, like a knot in fabric that never smoothed out. Skeptics argue it might just be a statistical fluke. After all, in a universe as vast as ours, some anomalies are bound to appear, but the cold spot continues to resist easy explanation. At Infinity Beyond, we explore such anomalies not just because they're strange, but because they could be clues. If the cold spot is real, if it points to something beyond the standard model of cosmology, then it could be the crack in the door to new physics, or even new universes. The universe speaks in patterns, in background radiation, galaxy distributions, and gravitational ripples. When one of those patterns is broken, it's worth paying attention, because sometimes the quietest parts of the cosmos whisper the loudest truths. We often think of black holes as eternal, cosmic monsters that devour matter and never let it go. But even the most powerful objects in the universe eventually fade. Yes, even black holes die. And when they do, it may mark the final chapter in the story of the cosmos. This concept was first introduced by physicist Stephen Hawking in the 1970s with his groundbreaking theory of Hawking radiation. He proposed that black holes aren't entirely black. Instead, they slowly emit particles, leaking energy due to quantum effects at the event horizon. Over unimaginable timescales, this slow radiation causes black holes to shrink, evaporate, and ultimately disappear. Let's put that into perspective. A small black hole might take trillions of years to vanish. A supermassive one? Over 100 years. A number so large, it dwarfs the current age of the universe. But eventually, in a distant, frozen future, the last black hole will emit its final particle. and vanish into darkness. What happens then? This marks the beginning of what scientists call the dark era, a time when no stars shine, no galaxies exist, and only low-energy particles drift endlessly in silence. There will be no light, no heat, no movement. The universe will reach a state of maximum entropy, known as the heat death, where nothing more can happen because there's no usable energy left. Some physicists believe this will be the true end. Others suggest strange quantum effects may allow for new universes to spawn, or even information to survive through quantum fluctuations. At Infinity Beyond, we ask, what does it mean when everything dies? When time stretches into near-eternal stasis, and only the memory of creation remains? There's beauty in this final silence, because it means everything that ever lived, everything that ever loved, once burned so brightly that even the darkness remembers. And perhaps that's the ultimate legacy of our universe, that it was, however briefly, alive. When we look at the sky, it appears calm, a quiet expanse of twinkling stars. But the reality is far more dramatic. Our galaxy is a battlefield, scarred by ancient collisions, shaped by cataclysms billions of years in the making. These events didn't just happen and vanish, they left behind a cosmic footprint. One of the most astonishing discoveries in recent astrophysics is that the Milky Way is not a static structure. It's alive. It writhes, pulses, and trembles, as if reacting to something long gone but not forgotten. In the last decade, researchers have uncovered evidence of waves rippling through the Milky Way's disk. These aren't ordinary waves. They're enormous vertical displacements, where millions of stars rise and fall like tides. But what caused them? A leading theory points to the Sagittarius dwarf galaxy, a much smaller galaxy that has collided with the Milky Way multiple times. Imagine a pebble dropped into a calm pond. That's what the Sagittarius dwarf did to our galaxy, sending out waves that are still moving through us today. These interactions leave permanent marks, distorted star motions, dense clusters in unexpected places, and a galactic disk that ripples like fabric in the wind. The stars remember. With high-precision data from missions like Gaia, we can now map these stellar motions with incredible detail. Scientists have found entire groups of stars, once thought to be random, that are moving together in distinct wave-like patterns. It's as if the galaxy still echoes from the impact. But it goes deeper than just motion. These collisions may have triggered bursts of star formation, lighting up regions of the galaxy in brilliant waves. They may even have shaped our solar system's very orbit within the Milky Way. And here's where it gets more mysterious. Some of these motions cannot be explained by known galactic interactions. Could there be another invisible force at work? Perhaps a massive dark matter structure we haven't yet mapped? Or remnants of even older collisions lost to time? The cosmos has memory, a long, sprawling one. And the Milky Way, like a great storyteller, carries its scars in silence, waiting for us to learn its language. At Infinity Beyond, we believe that every ripple, every unexpected motion, is a clue, a piece of a story written in stars and gravity. We are not just observers of the galaxy. We are passengers riding its waves, shaped by its past. The next time you look at the stars, remember, they are moving, dancing to ancient rhythms. And in that dance lies the tale of a galaxy that never forgets. We often imagine space as empty, a silent, still void where galaxies float at random. But what if that's not true? What if galaxies are drifting, not aimlessly, but along invisible currents? These are known as cosmic flows, and they reveal a deeper structure of motion across the universe. You see, galaxies don't just sit still in space. In addition to the general expansion of the universe, what we call the Hubble flow, many galaxies have their own peculiar motions. These movements aren't random. They are driven by massive gravitational forces pulling and pushing them through space. These directional movements are known as bulk flows, coordinated motions of large groups of galaxies. When astronomers study these patterns, they find that galaxies over hundreds of millions of light-years appear to be moving together towards something. But toward what? Some flows lead to massive structures like the Great Attractor or the Shapley supercluster, which we've explored in previous segments. Others are more mysterious, hinting at gravitational influences that stretch beyond our observable universe. One particularly puzzling phenomenon is the dark flow. Observed using data from the cosmic microwave background, it suggests that galaxy clusters are moving in a consistent direction, possibly due to forces from outside the visible cosmos. Yes, you heard that right. Some scientists believe the universe may be reacting to gravitational sources beyond what we can detect, potentially connected to a multiverse or a larger cosmic topology we don't yet understand. Even within our observable domain, cosmic flows help map out the structure of dark matter. Galaxies follow the gravitational contours of the cosmic web, sliding along its filaments, drawn to dense nodes and pushed away from great voids. At infinity beyond, we see these flows as the universe's circulatory system, carrying galaxies like blood through veins of gravity. They offer insight into the distribution of matter, the shape of the universe, and even the nature of dark energy. Mapping these flows isn't easy. It requires precise redshift measurements, velocity data, and advanced simulations. But as technology improves, we're beginning to chart the currents of the cosmos, like ancient mariners mapping ocean tides. These aren't just random motions, they're messages. The universe isn't just expanding, it's moving, breathing, flowing in a grand cosmic rhythm. The question is, where is it all going? If you've been following Infinity Beyond, you know that the cosmos never ceases to amaze. Today, we delve into an astonishing discovery, subtle ripples flowing through the Milky Way galaxy. These aren't just poetic metaphors, they are real, physical distortions in space, and they tell a much deeper story. On very small scales, gravity behaves as we expect it to. But as we observe the universe on vast cosmic scales, we notice something strange. Gravity alone cannot explain what we see. There seems to be an invisible actor influencing galaxies, guiding them, shaping them, perhaps even holding them together. Some regions in space exhibit peculiar motions, as though they're being nudged by a massive but unseen presence. Together with a sufficiently large mass, these regions create gravitational effects that cause stars to oscillate, ripple, and cluster in mysterious patterns. Recent studies reveal that the Milky Way has ripples, not just in its visible arms, but deep within its very structure. Imagine tossing a stone into a still pond and watching the water ripple out. Now imagine that pond is made of stars, dust, and dark matter, and that someone or something has tossed a cosmic stone. These ripples are not random. They may have been caused by something massive, perhaps a dwarf galaxy that passed through us long ago, or the gravitational remnants of an ancient collision. These ripples are frozen in time, embedded in our galactic fabric, whispering secrets from billions of years ago. In some regions of the Milky Way, astronomers have detected anomalies where stars are packed more tightly or moving at odd speeds. These aren't accidents. They may be echoes of galactic mergers or evidence of a deeper, darker architecture beneath the stars, possibly influenced by dark matter or even unknown physics. And here's the twist. These findings might only scratch the surface. The tools and data we have today, especially from missions like Gaia, have opened our eyes to a dynamic galaxy that is far from stable. It pulses, it breathes, it changes. Could it be that we are living in a galaxy still reverberating from past galactic interactions? Are we witnessing the aftershocks of a cosmic event, like two galaxies colliding and settling into harmony? Or is there something even more mysterious at play? At Infinity Beyond, we aim to take you deeper, past the stars you see, into the patterns you can't. Because only when we look closely at the ripples can we begin to understand the forces that shaped our place in the universe. So stay curious. The universe is speaking, and the Milky Way's ripples might just be its quiet song. Imagine trails of stars arcing gracefully through the galaxy, long, elegant streams that stretch across tens of thousands of light-years. These aren't just random alignments. They are the shattered remains of ancient star clusters and dwarf galaxies, slowly being pulled apart by the Milky Way's immense gravity. These stellar streams are more than beautiful. They're forensic evidence, cosmic breadcrumbs that help astronomers map the invisible shape of our galaxy. In fact, they may be the key to revealing the dark matter distribution that gives the Milky Way its structure. As these star clusters orbit the galactic center, tidal forces stretch them out, leaving behind narrow, curved trails. Over billions of years, what once was a tight-knit group becomes a ribbon of stars winding through space. Thanks to missions like Gaia, astronomers have identified dozens of these stellar streams. Some, like GD1 and the Palomar 5 stream, have become famous for their graceful arcs and surprising irregularities, kinks, gaps, and bends that hint at interactions with dark matter clumps. Each stream acts like a probe, a string vibrating in response to unseen masses. If a stream has a sudden bend or is missing a section, it could mean a dense object passed nearby, perhaps a rogue black hole or a chunk of dark matter with no visible counterpart. This is what makes stellar streams so exciting. They allow us to study things we cannot see. They help us test models of dark matter, the shape of the galactic halo, and even the presence of satellite galaxies too faint to detect directly. And there's more. Some streams appear to originate far outside the Milky Way's disk, suggesting ancient mergers with entire dwarf galaxies. In a sense, these are the scars of the Milky Way's violent growth, the remnants of cosmic cannibalism. At Infinity Beyond, we view these star streams not just as relics, but as tools, instruments playing the hidden music of the galaxy. Their patterns tell us where mass is concentrated, where distortions occur, and what lies beneath the starlight. The next time you see a stunning image of the Milky Way, know this: beneath that glowing band of stars lies a complex architecture, a skeletal framework etched by time, gravity, and destruction. We are only beginning to read this celestial map, and every stream we trace brings us closer to understanding the true nature of our galactic home. In the vast emptiness of the universe, galaxies appear serene, floating islands of stars, peacefully drifting in space. But behind that calm exterior lies a violent truth. Galaxies eat each other. This cosmic behavior is known as galactic cannibalism, and it's more common than you might think. The Milky Way itself is guilty. Over billions of years, it has consumed smaller dwarf galaxies, ripping them apart with gravitational tides and absorbing their stars, gas, and dark matter. Evidence of these cosmic meals still lingers in the form of stellar streams, twisted arms, and oddly behaving star clusters. But the Milky Way isn't just a predator, it's also a future victim. In approximately 4 billion years, our galaxy will collide with the Andromeda Galaxy, another massive spiral moving toward us at 110 kilometers per second. The result will not be an explosion, but a gravitational dance that lasts for billions of years, reshaping both galaxies into something new, a single, giant, elliptical galaxy. So how does galactic cannibalism actually work? When a smaller galaxy ventures too close to a larger one, tidal forces stretch and distort it, pulling stars out of their original paths. These stars often spiral into the larger galaxy's halo, where they remain as ancient evidence of the merger. Sometimes entire cores of dwarf galaxies survive the initial encounter and continue orbiting their captor. becoming satellite galaxies like the Magellanic Clouds, which now orbit the Milky Way. But cannibalism doesn't just feed mass, it fuels evolution. These collisions can trigger massive starbursts, light up dormant black holes, and even give birth to new galactic structures like rings or thickened disks. The process also accelerates the growth of supermassive black holes. As galaxies merge, their central black holes spiral toward one another, eventually colliding in a burst of gravitational waves, an event that ripples across the fabric of space-time. At infinity beyond, we see galactic cannibalism not as destruction, but as rebirth. A necessary process in the life cycle of the cosmos, one that reshapes matter, creates new stars, and forges the grand architecture of the universe. The sky above us may look quiet, but it's a battlefield written in starlight, a place where galaxies collide, consume, and evolve. Across the vast emptiness of space, not everything that shapes the universe can be seen. Some forces leave no visible trail, yet their influence echoes through time. These are the galactic ghosts, ancient, invisible structures that continue to sculpt the motions of stars and galaxies. Recent studies suggest that certain regions of space contain gravitational anomalies, places where stars accelerate, decelerate, or drift in ways that defy current models. It's as if something massive is lurking nearby, but we can't see it. These ghost structures may be the remains of long-lost galaxies, devoured and torn apart by larger ones like the Milky Way. While their stars have been absorbed or flung across space, their gravitational signatures linger, like fingerprints on glass. The European Space Agency's Gaia mission has helped map these ghost trails. One such structure is the Gaia Sausage, a stellar stream believed to be the remnants of a galaxy that collided with the Milky Way billions of years ago. Its stars now orbit in a peculiar pattern, distinct from the rest of the galactic disk. But the Gaia Sausage is just one of many. Across the sky, we're finding stellar streams and gravitational distortions that hint at a hidden history of mergers and cosmic violence. Every ripple, every deviation, tells a story of a galactic encounter long forgotten. More than just relics, these ghost structures may actively shape the future. They can distort the orbits of stars, influence the formation of new stellar systems, and even guide the motion of entire star clusters. And it gets stranger. Some anomalies cannot be linked to any visible source. No star stream, no gas cloud, no known object. Could they be the fingerprints of dark matter clumps? Or remnants of ancient structures that never formed into galaxies as we understand them? At Infinity Beyond, we explore these mysteries with a deep sense of wonder. The idea that our galaxy is haunted, not by spirits, but by the gravitational echoes of forgotten giants, is both poetic and profound. These ghosts remind us that the universe is not static. It is a living archive, and every star is part of a vast, dynamic record. So the next time you gaze at the night sky, remember, some of the forces guiding those stars aren't visible, but they are there, silent, massive, and ancient. We live inside the universe, a three-dimensional space filled with stars, galaxies, and mystery. But have you ever wondered, what shape is the universe itself? Is it flat like a sheet, curved like a sphere, or saddle-shaped like a cosmic roller coaster? And what does that mean for infinity? To answer this, cosmologists rely on deep observations of the cosmic microwave background, CMB, the afterglow of the Big Bang. By analyzing how light curves across vast distances, scientists can infer the geometry of space. Here's what they've found. 1. Flat universe. Current data, especially from the Planck satellite, strongly suggest that space is flat, with less than 0.4% margin of error. That means, on the largest scales, the angles of a triangle add up to 180 degrees, and parallel lines never meet. A flat universe could extend forever, infinite in all directions. But it could also be topologically looped, like a game map that wraps around itself. Even flatness doesn't guarantee true infinity. 2. Spherical, closed universe. In a positively curved universe, space wraps around itself like the surface of a sphere. If you traveled far enough in one direction, you'd eventually end up where you started, without ever hitting a wall. A closed universe would be finite in volume, but boundless in structure. And such curvature could eventually reverse expansion, leading to a big crunch. 3. Hyperbolic, open universe. Alternatively, a negatively curved or saddle-shaped universe would expand forever and accelerate, with parallel lines diverging and triangles having less than 180 degrees. It's infinite, chaotic, and exotic, a cosmic shape that's hard to visualize but rich in possibility. So, which is it? Right now, all evidence points to flatness, but that doesn't mean the story is over. Tiny curvature might still exist just beyond our detection threshold, and subtle topology could make a flat universe feel finite in strange ways. Moreover, some inflation models predict that local flatness is just a side effect. The universe could still be curved on larger, unseen scales. And string theory allows for extra dimensions that curve space in ways we can't yet observe. At infinity beyond, we ask not just what shape is space, but what does that shape mean for time, for infinity, and for the possibility of other worlds? If space is flat and infinite, then there could be infinite copies of you scattered across the multiverse. If space is closed, then everything is connected in a loop. If space is open, then the cosmos may expand into endless strangeness. And in all three cases, one truth remains. You are living inside geometry, and the universe, whatever shape it takes, is the grandest design ever drawn. As we drift through the universe aboard the Milky Way, we imagine our galaxy is simply orbiting the center of its own mass. But in truth, we are moving, fast, towards something immense and mysterious. An invisible force is tugging at us, at our neighboring galaxies, and even entire superclusters. That force has a name: the Great Attractor. Discovered in the 1980s, the Great Attractor is a region of space that seems to be pulling galaxies toward it with gravitational strength beyond anything nearby. The Milky Way, the Andromeda Galaxy, the Virgo supercluster, all are moving toward this point at incredible speeds of over 600 kilometers per second. But here's the mystery. We don't know exactly what it is. The Great Attractor lies in a region of space called the Zone of Avoidance, a part of the sky obscured by the dust and gas of our own galaxy. For decades, this cosmic curtain has blocked our direct view. Yet through indirect measurements, redshift surveys, radio telescopes, and X-ray data, we've begun to peer behind the veil. What we found is a massive concentration of galaxies, clusters upon clusters, bound together in what's known as the Laniakea supercluster, a colossal structure encompassing over 100,000 galaxies. And at the gravitational center of this supercluster lies the Great Attractor. But some researchers believe there's even more to the story. A deeper, darker mass may lurk behind the Great Attractor, an even greater force known as the Shapley supercluster, possibly contributing to our motion through space. Could this region be a hidden node in the cosmic web, a place where dark matter, regular matter, and ancient gravitational flows converge? Or is it something altogether unknown? A relic of the early universe, a collapsed region of space, or even an observational illusion caused by distortions in the cosmic microwave background? At Infinity Beyond, we chase these gravitational mysteries because they tell us something profound. The universe is not still. It's in motion. And so are we, drawn towards something vast and unseen, something that challenges our perception of what lies ahead. We may never arrive at the Great Attractor. The expansion of the universe pulls us apart faster than gravity can bring us together. But the fact that we feel its tug across hundreds of millions of light-years reminds us how deeply connected all galaxies truly are. Long before galaxies formed, before stars ignited, before planets were born, the universe was a dense, hot ocean of particles and energy. And from that chaos emerged something truly extraordinary: sound. Yes, the early universe rang with the first echoes of existence, and today we can still hear them. This cosmic sound isn't like anything we hear with our ears. It's the cosmic microwave background, the oldest light in the universe, a faint glow that bathes all of space. But embedded within this glow are subtle fluctuations, pressure waves that represent actual sound vibrations from the infant universe. So what made the universe ring? In the first 380,000 years after the Big Bang, the universe was a plasma, a dense mix of light and matter where photons constantly scattered off electrons. This churning environment created pressure, like in the interior of a star, and that pressure generated acoustic waves, ripples that propagated through space like sound through air. These are known as baryon acoustic oscillations, and they tell us more than you might think. By measuring these ancient sound waves, scientists have been able to map the distribution of galaxies across vast distances. These echoes serve as a cosmic ruler, helping us measure how fast the universe is expanding and how much dark energy might exist. And the patterns of these sound waves also give us insight into the initial conditions of the universe, how matter was distributed, how gravity worked in those earliest moments, and even how quantum fluctuations gave rise to everything we see today. It's incredible to realize that the universe, seemingly silent and still, carries within it the fingerprints of ancient sound. And though space is now too thin to carry pressure waves like it once did, the memory of that cosmic symphony remains. Some researchers have even converted these primordial oscillations into audible sound, deep, rumbling tones that increase in pitch as the universe expands. In just a few seconds of playback, we can hear a billion years of evolution. At infinity beyond, we listen to the universe not just with eyes and telescopes, but with imagination. We ask, what else does the universe remember? And how do those memories shape what it is today? The early universe didn't just flash into light, it sang. And the echoes of that song are still with us, whispering through the microwave background, guiding galaxies and unlocking the secrets of time itself. Picture a vast, three-dimensional web stretching across the entire universe, a cosmic framework connecting galaxies, clusters, and voids. This isn't just an artistic idea, it's real. Scientists call it the cosmic web, and it may be the most important structure in the universe that you've never seen. At the grandest scale imaginable, the universe isn't randomly arranged. Galaxies form along gigantic filaments of dark matter and gas, intersecting at dense nodes known as galaxy clusters. In between these strands lie immense voids, cosmic deserts where few galaxies exist at all. This cosmic web is not only beautiful, it's functional. It acts like a highway system for matter, energy, and even galaxies themselves. Galaxies don't just form anywhere. They form along these filaments, drawn by gravity to the densest intersections. But how do we know it exists if we can't see it with our eyes? Astronomers use massive sky surveys, such as the Sloan Digital Sky Survey, SDSS, to map the locations of millions of galaxies. When plotted in 3D, a striking pattern emerges: clusters and filaments repeating like neural connections in a brain. In fact, some scientists have compared the cosmic web to biological networks, like the neurons of a human brain. This similarity is more than visual. The way matter flows, connects, and distributes across the universe resembles the way information travels through neural systems. Dark matter is believed to be the backbone of this web. Its gravitational pull sculpts the strands and determines where galaxies can form. Ordinary matter, gas, dust, stars, flows into the gravitational wells created by these dark matter filaments. But the cosmic web isn't static. It evolves. Over billions of years, galaxies migrate along these filaments. Some collide. Others get stretched and flung into the void. Even supermassive black holes at galactic centers may grow by feeding on matter drawn in through these cosmic connections. What's more, astronomers now believe that the cosmic web may carry not just matter, but magnetic fields, threads of force that span millions of light years. This could have major implications for how energy moves through space and how galaxies grow and rotate. At Infinity Beyond, we ask, could the cosmic web be more than a structure? Could it be a kind of nervous system for the universe? A network that determines how the cosmos thinks, breathes, and evolves? The next time you look at a map of galaxies, know this: you're not just seeing dots. You're seeing the outline of a vast, invisible architecture, a web that holds everything together, from the smallest particles to the largest clusters of galaxies. It's almost impossible to imagine that everything we see today, galaxies, stars, planets, and even ourselves, originated from tiny, random quantum fluctuations smaller than an atom. Yet, this is one of the most profound ideas in modern cosmology. At the beginning of time, during the inflationary epoch, a fraction of a second after the Big Bang, the universe expanded at a rate faster than the speed of light. And during that unimaginably brief moment, the quantum foam, tiny fluctuations in energy, was stretched across the cosmos. These fluctuations were minute differences in energy density, born from the uncertainty inherent in quantum physics. Left to themselves, they would have remained microscopic. But because of inflation, they were blown up to cosmic scales, becoming the seeds of all future structure. Imagine ripples in a pond, frozen and magnified to become the layout of the entire ocean. That's what inflation did to quantum fluctuations. As the universe cooled, these tiny over- and under-dense regions acted like gravitational wells. Matter was drawn into them, and over billions of years, they grew into stars, galaxies, clusters, and the vast web-like structure of the universe we see today. These initial seeds are visible in the cosmic microwave background as faint temperature variations, places where more matter collected versus where it didn't. With high-precision instruments like the Planck satellite, we can now measure these differences to an astonishing degree, mapping the universe's blueprint just moments after it began. What's even more astonishing is that this idea links the smallest scales of physics, quantum mechanics, with the largest structures in existence. It's a direct bridge between particle physics and cosmology. But the mystery deepens. We still don't fully understand what drove inflation, what caused it to start, or stop, or even whether it happened once or cyclically. Some theories suggest the inflaton field, a hypothetical quantum field responsible for this expansion. Others hint at connections to string theory or multiverse models, where inflation never ends and new universes are constantly being born. At Infinity Beyond, we ask, if the universe was born from uncertainty, from randomness, then is everything we see today a result of cosmic chance? Or was there a deeper rule, a hidden order beneath the quantum storm? The next time you look at the stars, remember this. They may owe their existence to a random fluctuation in energy at the dawn of time. From the tiniest tremble came everything. We often imagine galaxies as still and serene, slowly spinning through the void. But new discoveries paint a radically different picture. The Milky Way, our home galaxy, may actually be pulsing, breathing, reacting, almost alive. Recent data from the European Space Agency's Gaia mission reveals something astonishing. The stars in our galactic disk aren't just rotating, they're oscillating. Like waves on an ocean, they rise and fall through the galactic plane in rhythmic, wave-like patterns. These aren't random fluctuations. They form large-scale structures, vertical waves that span tens of thousands of light years. It's as if the Milky Way experienced a massive jolt in the past and is still reverberating with the aftershocks. So, what could have triggered such a disturbance? One possibility is a collision with a smaller galaxy, like the Sagittarius dwarf that passed through the Milky Way's disk. This would be like a stone dropped into a cosmic lake, sending ripples throughout the entire structure. Another idea is that these waves are the result of dark matter clumps, invisible pockets of gravitational force, passing near the galactic disk and nudging the stars with their unseen hands. Regardless of the cause, these waves challenge our understanding of galactic dynamics. We used to think galaxies were relatively stable systems. Now we see them as complex, responsive, and surprisingly sensitive to their environment. It's more than just poetic metaphor. If the Milky Way is pulsing, it could affect everything from star formation to the stability of planetary systems, including, potentially, our own solar neighborhood. At Infinity Beyond, we ask, if our galaxy has a heartbeat, what does it mean for us? Could these waves influence life over cosmic timescales? Could they be part of a larger pattern? A rhythm shared by all spiral galaxies? And here's another question. Are we at the beginning of a new pulse, or the fading echo of an ancient galactic song? One thing is clear, the Milky Way is not a silent, still entity. It lives, it reacts, it carries the memory of ancient collisions and responds with waves that ripple across the stars. Our galaxy has a story, and it's written not in ink, but in motion. Imagine if the universe had a soundtrack, not of music or voices, but of ripples in space-time itself. That's not fantasy, it's real. They're called gravitational waves, and they've changed the way we listen to the cosmos forever. First predicted by Albert Einstein in 1916, gravitational waves are distortions in the fabric of space-time, caused by the most violent and energetic events in the universe. Colliding black holes, merging neutron stars, supernova explosions. These cosmic cataclysms send waves across the universe, stretching and squeezing space itself. For over a century, they remained undetectable, until 2015. That year, the LIGO Observatory made history by detecting gravitational waves for the first time, from two black holes merging over 1 billion light-years away. It was the first time humanity heard the universe in a new way, not through light, not through particles, but through ripples in reality. These waves are incredibly subtle, changing the length of a laser beam by less than the width of a proton. And yet, they carry massive amounts of information. Through gravitational wave astronomy, we've opened an entirely new window into the universe. We can now detect objects we can't see. Black holes in the dark, neutron stars surrounded by no light at all. We can even test the limits of Einstein's relativity, search for the nature of gravity itself, and possibly detect primordial waves left over from the Big Bang, the universe's first tremble. And we're just getting started. Future observatories like LISA, Laser Interferometer Space Antenna, will launch into orbit, detecting lower-frequency gravitational waves from massive black holes millions of times the mass of the Sun. Some even believe gravitational waves could help us detect wormholes, cosmic strings, or evidence of higher dimensions, things we can't probe with light alone. At Infinity Beyond, we believe the universe speaks many languages: light, matter, magnetism. But gravitational waves are its heartbeat, a silent rhythm that reveals the hidden choreography of space, time, and energy. Now that we can listen, What else will the universe sing to us? Everything that begins must end, even the universe itself. But what does it mean for everything to end? No more stars, no more light, no more time. Today on Infinity Beyond, we explore the chilling possibilities of how the cosmos may one day die. There are several competing theories, each one more mind-bending than the last, and all depend on the universe's energy content, geometry, and the mysterious force we call dark energy. Let's start with the most accepted scenario, the Big Freeze. As the universe continues expanding at an accelerating rate, galaxies will drift farther and farther apart. Eventually, distant galaxies will vanish beyond our observable horizon, too far for their light to ever reach us. Stars will exhaust their fuel. New star formation will cease. Black holes will be the last to remain, quietly evaporating over trillions of years via Hawking radiation. The universe will go dark, cold, and silent, a state known as heat death, where entropy reaches its maximum and no useful energy remains. In this version, time doesn't end, but meaningful change does. A universe without contrast, without structure, without memory. But what if the expansion doesn't just continue? What if it accelerates uncontrollably? The Big Rip. In this more dramatic scenario, dark energy becomes increasingly powerful, tearing apart galaxy clusters, then individual galaxies, stars, planets, and even atoms. Eventually, space itself is ripped apart. Time ceases to function. Physics as we know it breaks down. We don't know if dark energy behaves this way, but if it does, the Big Rip could arrive in tens of billions of years. Then there's an older, once popular idea, the Big Crunch. If gravity were strong enough to halt expansion, the universe might reverse, collapsing back in on itself. Galaxies would merge, temperatures would soar, and space would shrink until all matter converges into a final singularity. Some versions of this theory suggest a rebirth, a cyclic universe that expands and contracts eternally, perhaps even spawning new realities each time. This leads us to the Big Bounce here. The universe never truly ends. Instead, it oscillates, bouncing between big bangs and big crunches in an infinite loop. Each cycle erases the previous one, creating a cosmic amnesia. And finally, the most exotic possibility: vacuum decay. Quantum theory allows for the idea that we live in a false vacuum, a metastable state that could suddenly collapse into a lower-energy true vacuum. If that happens, a bubble of destruction would expand at the speed of light, rewriting the laws of physics in its wake. Instant, undetectable, inevitable. Maybe tomorrow, maybe in 1 trillion years. At Infinity Beyond, we explore these endings not to frighten, but to marvel. The universe may die, but its story is worth telling. And the more we understand its fate, the better we understand our place within it. Because the end of time isn't just about destruction. It's a reminder to make this moment meaningful. Gravity. It's the force that binds us to the Earth, keeps the planets orbiting the Sun, and holds galaxies together. But at the scale of the entire universe, gravity doesn't just shape structure, it shapes destiny. The fate of everything we see is tied to how gravity battles against the universe's expansion. You've likely heard that the universe is expanding. Space itself is stretching, carrying galaxies farther apart over time. But this expansion is not constant. It's a battle between gravity, trying to pull everything back together, and something else, pushing it apart. That something else is known as dark energy, a mysterious force responsible for the accelerating expansion of the universe. But long before dark energy dominated, gravity was in charge, forming stars, galaxies, and clusters from the primordial soup of the Big Bang. The early universe was a playground of gravitational competition. Regions with slightly higher density collapsed under their own gravity, forming galaxies. Others remained empty, creating the vast cosmic voids we observe today. But what about the long-term picture? If gravity were stronger than dark energy, it could have halted the expansion, even reversed it, causing the universe to eventually collapse in a big crunch. On the other hand, if dark energy wins completely, the universe may accelerate forever, ending in a big freeze or perhaps a big rip, where even atoms are torn apart. Current evidence suggests we're headed toward an ever-accelerating expansion, a slow, cold fade into darkness, where galaxies drift so far apart that light can no longer travel between them. But nothing in cosmology is set in stone. In fact, gravity continues to surprise us. Recent discoveries show that gravitational waves, ripples in space-time caused by massive collisions, may play a larger role in transferring energy than we once thought. These waves stretch across the cosmos, carrying the fingerprints of violent events like black hole mergers and neutron-star collisions. And gravity may not behave the same everywhere. Some theories suggest it could vary across large distances or change depending on the density of matter. If true, it could rewrite our understanding of cosmic expansion and the universe's fate. At infinity beyond, we see gravity not just as a force, but as a storyteller. It sculpts galaxies, governs the life cycles of stars, and silently decides how the cosmos will end. Whether we face a cold death, a fiery collapse, or something far stranger, one thing is clear: the universe is a dynamic, evolving entity, and gravity is at the heart of it all, a quiet architect with the power to shape everything. It sounds like science fiction, the plot of a movie. But more and more scientists are asking the question seriously: are we living in a simulation? This idea, known as the simulation hypothesis, suggests that our universe, our reality, might be an artificial construct, designed and run by an advanced intelligence. And disturbingly, we might not be able to tell the difference. Let's explore the logic. In 2003, philosopher Nick Bostrom proposed a powerful argument. If any civilization becomes advanced enough to create realistic simulations of universes, and if they create many of them, then the simulated beings vastly outnumber the originals. So statistically speaking, the odds that we are the original base reality become very low. We are more likely to be simulations within simulations. Still sounds far-fetched? Consider this. Video games today simulate entire planets. Artificial intelligence is learning to replicate human speech, behavior, and even creativity. Quantum computers are on the horizon. Now imagine a civilization thousands or millions of years ahead of us. Could they simulate a reality so perfect, so detailed, that the simulated beings, like us, believe it's real? But how would we know? Some physicists have suggested that the pixelation of space, tiny, indivisible units of space-time called the Planck length, could be like the resolution of the universe. If the universe is discrete, it might be running on a kind of code. Others explore anomalies in quantum physics, like wave function collapse, that seem to depend on observation, as if reality is being rendered only when measured, like in a video game. Even cosmic patterns, like the distribution of galaxies or the fine-tuned nature of physical constants, have been cited as potential signs of a designed system. But there's a deeper, more philosophical side. If the simulation is perfect and we can't detect it, does it even matter? At Infinity Beyond, we ask not just whether reality is simulated, but why the question matters. If we are in a simulation, who or what created it? For study, for entertainment, for evolution? And if we're not, then what does it mean that our world is so computational, so mathematical, and so elegant, as if it was written, not just formed? Whether reality is base level or rendered, one thing is clear. It is stranger, deeper, and more mysterious than we ever imagined. And in that mystery lies purpose. We often speak of the Big Bang as the beginning of everything: time, space, matter, and energy. But one question continues to haunt science and philosophy alike. What came before the Big Bang? And perhaps more importantly, can we ever know? The standard model of cosmology tells us that time itself began at the moment of the Big Bang. Asking what came before is, under this view, like asking what's north of the North Pole. It may be a question without meaning, or is it? Recent theories suggest that the Big Bang may not have been the ultimate beginning, but rather a transition, a bridge from something else. Let's explore some of the leading ideas. The cyclic universe. One possibility is that the universe is eternal and cyclic, going through infinite phases of expansion and contraction. After each big crunch, a new Big Bang erupts, resetting the cosmic clock. This Big Bounce model suggests we're just one universe in an endless loop, and that time never truly began. It just repeats. The multiverse landscape. Another theory suggests our universe is just one bubble in a vast multiverse, a grand cosmic foam where universes pop into existence like quantum fluctuations. In this view, the Big Bang was a local event, the birth of our bubble. But others may have existed before, and countless more may exist now. This aligns with some models of eternal inflation, where space expands forever, but localized pockets collapse into their own Big Bangs. Before our universe, there could have been an infinite sea of bubbling possibilities. Quantum gravity and loop time. Quantum gravity theories, such as loop quantum cosmology, attempt to unify general relativity with quantum mechanics. In these models, space-time is not continuous, but made of discrete loops. The Big Bang becomes a bounce from a previous contracting phase, implying there was indeed a before. Time emergence hypothesis. Some physicists propose that time itself is not fundamental, but emergent, a property that arises only when matter reaches certain complexity. In that case, the universe before the Big Bang may have been timeless, a realm of pure quantum potential, waiting for structure to emerge. And finally, there's the philosophical frontier. Maybe we're asking the wrong question. Maybe before only makes sense within time. And trying to apply it outside the context of our physical universe is like trying to smell the color blue. At infinity beyond, we believe the question isn't just scientific. It's existential. What existed before the Big Bang may reveal not only the nature of time, but the very nature of reality itself. Perhaps the ultimate origin isn't something we'll find in equations, but in the space between science, imagination, and wonder. After exploring black holes, dark matter, cosmic webs, and the edges of time itself, one question remains. Why does the universe exist at all? It's not just the laws, the particles, the galaxies. It's that they exist in such perfect harmony, balanced on the edge of chaos, yet fertile enough for life, thought, and meaning to emerge. We've searched for beginnings, for endings, for life. We've asked what came before time, and what will come after it. And with each answer, we've only found deeper questions. Some scientists say the universe is mathematical, a grand equation. Others say it's biological, evolving like a living system. Philosophers suggest it might be conscious, or a story, or even a dream dreamed by something far greater. But maybe the universe doesn't need to be solved. Maybe it was never meant to be understood like a puzzle, but experienced moment by moment. Because for all our telescopes and equations, the most extraordinary fact is this: you are here, made from the ashes of stars, alive in a universe where you can ask these questions, feel wonder, and reach beyond yourself. You're not just observing the cosmos. You are part of it, an expression of its endless curiosity. And as long as questions remain, as long as we look up and wonder, the story continues. At Infinity Beyond, our mission has never been to end the search, but to light the way. Because the universe isn't just big, it's not just strange, it's beautiful, and it's ours to explore together. From a distance, the universe looks chaotic, galaxies scattered like glitter on black velvet. But zoom out far enough, and something remarkable emerges. Order. Galaxies aren't randomly placed. They form a vast interconnected structure called the cosmic web. And what's even more mind-blowing, it looks eerily similar to the human brain. The cosmic web is made of filaments, thin strands of dark matter and galaxies, woven together in a vast network across the universe. Where filaments intersect, we find galaxy clusters, and between them lie enormous voids, cosmic deserts almost entirely empty of matter. Simulations show that this web was formed by the gravitational collapse of matter after the Big Bang. Tiny quantum fluctuations grew into tendrils, and those tendrils became the skeleton of the universe. But here's where things get truly strange. In 2012, scientists compared computer models of the neural network in the human brain to the large-scale structure of the universe. Despite the enormous difference in scale, one being micrometers, the other hundreds of millions of light-years, the patterns were strikingly similar. Both systems balance efficiency and connectivity. Both use a minimal amount of material to transfer a maximum amount of information or mass. And both evolve through local interactions that scale up into global structures. This has led some scientists and philosophers to ask bold questions. Could the universe be self-organizing like a neural network? Is consciousness a cosmic pattern, not just a biological one? Could intelligence itself arise from the structure of space and matter, not just matter arranged into brains? These are speculative questions, but they force us to consider something profound. That the universe might not just be matter and energy, but also information. In some theories, like digital physics, the universe is seen as a computational process, a giant simulation or mathematical structure, where information is the fundamental currency of reality. Even if we don't go that far, the similarities between the cosmic web and brain structure hint at a possible fractal principle, where nature repeats patterns from small to large scales. At Infinity Beyond, we believe that pattern is not coincidence. It's a clue that the universe, like the brain, may not just contain thought, but might be capable of something like thought. We are the universe looking at itself, and maybe, in some strange poetic way, it's thinking back.
When we look at the night sky, we think we're seeing the universe, but in truth, we're only seeing a tiny sliver of it. Most of reality is hidden, not because it's far away, but because it's invisible. Welcome to the invisible universe, a realm of energy, matter, and forces we can't perceive with our eyes, but that shape everything we know. Let's start with light itself. The human eye can detect just a narrow band of the electromagnetic spectrum, what we call visible light. But there's so much more. Infrared, which reveals the heat of stars and planets. Ultraviolet, which uncovers high-energy phenomena. Radio waves, which show the structure of galaxies. X-rays and gamma rays, which expose black holes and supernovae. Thanks to telescopes like Hubble, Chandra, James Webb, and ALMA, we can now see across the full spectrum, painting a much richer picture of the cosmos. But even beyond light, there's more that's hidden. Dark matter. We can't see it. We can't touch it. But we know it's there because its gravity bends light, holds galaxies together, and shapes the cosmic web. Dark matter makes up about 27% of the universe. That's 5 times more than all visible matter combined. Dark energy. Even more mysterious is dark energy, a force pushing the universe to expand faster and faster. It accounts for about 68% of the cosmos, and we have no idea what it really is. Add it up. 95% of the universe is invisible, untouchable, unexplained. Even within our own galaxy, dust clouds block visible light. Some of the most massive stars and black holes are completely obscured, but with infrared and radio, we can peer through the veil. And it's not just about detection, it's about translation. The colors in JWST images aren't real, they're interpretations. We assign colors to different wavelengths to visualize what's normally beyond human sight. In essence, we're building new senses, machines that let us hear in light, see in gravity, and touch the untouchable. At Infinity Beyond, we explore not just what the universe shows us, but what it hides, and why that matters. Because sometimes, the most powerful truths are the ones we can't see yet.
When we gaze into the night sky, we're not just looking across distance, we're looking back in time. The farther away an object is, the longer its light has taken to reach us. But this raises a profound question. Is there a limit to what we can see? And what lies beyond that limit? That limit is called the cosmic horizon, the edge of the observable universe. It's the farthest distance from which light has had time to reach us since the Big Bang, about 46.5 billion light-years in every direction. That's our cosmic bubble. But the key word here is observable. The universe itself may be vastly, even infinitely, larger than what we can see. Our observable patch is just one region in a potentially boundless sea of galaxies, clusters, and cosmic web filaments stretching far, far beyond the reach of light. So what's beyond the cosmic horizon? There are a few possibilities. 1. More of the same. Many cosmologists believe that the universe beyond what we can see looks much like our own, filled with galaxies, stars, and cosmic structures. If true, we're just a small patch in an enormous homogeneous universe. 2. Different laws of physics. But some theories propose that beyond our horizon, the rules might change. Constants like the speed of light, gravity, or even fundamental particles could vary, giving rise to pocket universes with radically different physics. This idea links to the inflationary multiverse, where quantum fluctuations during the Big Bang produced separate regions, each with its own version of reality. 3. Bubble universes and cosmic collisions. If our universe is a bubble, it may have collided with others in the past. Some researchers have even searched the cosmic microwave background for circular patterns, bruises, where our universe might have bumped against another. Though no definitive evidence has been found, the possibility remains one of the most tantalizing in modern cosmology. 4. A finite universe with a boundary. Alternatively, some theories suggest the universe may be finite, curved in such a way that if you traveled in one direction long enough, you'd return to your starting point, like a 3D version of the surface of the Earth. In that case, the edge isn't an edge at all, but a loop. Beyond the horizon might simply be more of us, wrapped around space itself. At Infinity Beyond, we explore these boundaries, not to find walls, but to understand what freedom truly means on a cosmic scale. The edge of what we can observe is not the edge of existence. It's just the frontier of our knowledge, a moving boundary, expanding every day with each new telescope, theory, and question. What lies beyond? Maybe more galaxies, maybe new physics, maybe a reflection of ourselves, or maybe something we're not yet ready to imagine. As powerful as our telescopes are, there is one part of the universe that has remained frustratingly hidden. A region of the sky shrouded by dust, gas, and billions of stars. An area astronomers call the zone of avoidance. It's not a term rooted in fear, but in reality. When we look at the sky in optical wavelengths, the central band of the Milky Way is so densely packed that it blocks our view of what lies behind it. For decades, this strip, covering about 10 to 20% of the sky, was essentially a blind spot in our cosmic map. But what if something massive is hiding there? What if behind the curtain of our own galaxy lies a structure that could change everything we think we know? That's not just speculation. The discovery of the Great Attractor, which we discussed earlier, came from analyzing galaxy movements that seemed to lead toward the zone of avoidance. It was like watching leaves move in the wind. We couldn't see the source, but we felt its pull. So how do we explore a region we cannot see? Astronomers have turned to infrared and radio waves, types of light that can pierce through the gas and dust. These tools have begun to reveal what's hiding behind the Milky Way: entire galaxy clusters, massive structures, and potentially threads of the cosmic web we couldn't detect before. One of the most significant findings is the Norma cluster, a dense region of galaxies partially obscured by the zone of avoidance. It appears to be one of the central components of the Great Attractor, helping explain the gravitational pull we feel across the universe. But there may be even more. The Shapley supercluster, for instance, is even farther away, but may contribute to the same pull. Some models suggest that we're being influenced by multiple dense regions, connected through hidden filaments of dark matter. At Infinity Beyond, we ask, if our view of the universe is blocked in one direction, how much are we missing? Could there be another Great Attractor? A dark galaxy? Or even a void so large that it warps nearby space? The zone of avoidance reminds us that even in the age of space, telescopes and galactic maps, mystery endures. There are still frontiers we haven't reached, not because of distance, but because of obstacles right in front of us. And as we peer deeper into these obscured regions, we may uncover truths that will reshape our entire understanding of the cosmos.